In this video, I'll talk through the 2022 Higher Chemistry paper. I'll explain how I would approach each question, starting off in multiple choice question number 1. Here, we're asked for an element that has covalent bonding and LDFs. First thing I would do is go to the melting points and boiling points page in the data booklet. We're asked about boron, sodium, neon, and sulfur. Everything on the left hand side are metallic bonding, so that will not be our answer. We have monatomic group 0 or group 8. Again, will not be our answer for this question. Comparing the two covalent chemicals, we have our higher melting points and boiling points for our covalent network. That leaves our sulfur as our covalent molecule. Going back to the question, cannot be B or C. Boron would be a network, therefore would not have LDFs. LDFs are an intermolecular force between molecules. You have to have molecules in the first place. And that means that sulfur would be our correct answer for this question. Next question, we are asked about successive ionization energies for an element, and we want to figure out the most stable ion formed by this atom. What stands out to me is that the first two ionization energies are pretty close, and then the third one is a lot higher. This would mean this is from an inner shell. Inner shell will be held more tightly, it will require more energy to take away. This would suggest that our outer shell is going to have 2 electrons in the outer shell. Once you've taken both of them out, you're then going to an inner, more tightly held electron. The first two are fairly easy to remove. Removing electrons would make it positive. 2 plus positive charge would be our correct answer for this one. Next question, we're asked about boiling points. Boiling points are again to do with intermolecular forces. This means that we are not talking about the covalent bonds that are internal. If something has a higher boiling point, that would mean that they would have stronger intermolecular forces or van der Waals forces. And D would be comparing intermolecular forces with intramolecular forces. Isn't what we're trying to do. C would be our correct answer. Moving on, talking about reducing agents. Reducing agents cause reduction in other substances. They will therefore lose electrons. The reducing agent itself would be oxidized. Electronegativity is to do with the attraction for electrons. If we have something that will easily give up electrons, it would likely have a low electronegativity. Therefore, B would be our right answer. Another way of approaching this is that our top right is our reducing agents. Bottom left of the table tends to be our oxidizing agents. We look at lithium's electronegativity, we'll see it's got a very low electronegativity, 1.0. And if it's got a low electronegativity, when it's paired up with something else, it will likely lose electrons to the other chemical. That'll give us B for answer. Next one, we're asked about the correct redox equation for iron 2 with acidified dichromate. When we go to the data booklet, we'll shuffle down back to this page. When it comes to the chromium, there's only one option for our dichromate. That is this one here. The key to this question is that has 6 electrons. For a redox equation to work, there also has to be 6 electrons in the other equation. One of the things that makes this one more complicated is the iron. There are a couple of iron equations that it could be. Got it going from 2 plus to no plus, 3 plus to no plus, or 3 plus to 2 plus. If we check the electrons in the top one, we've only got 2 electrons. If this was going to be our correct answer, we would have to times that by 3. And that will give you the 6 electrons we are after. Middle one has to be times by 2. The bottom one would need to be times by 6. What we now need to do is check which of the answers matches up to either the top one times by 3, middle one by 2, or the bottom one by 6. In this one, we've got 2 plus going to no plus. That would be our top equation. We would need 3 times as many. That rules out that answer. Get rid. Middle one, we've got 2 plus going to 3 plus. Only got one of them. That's the one at the bottom, which would need 6 of them. Again, that one can get chopped away. Next one, we've got 2 plus going to no plus. That is not needing 6 times as many as them. That's going to rule that one out. Whereas D has going from 2 plus, 3 plus. There's 1 electron involved, and we need to times it by 6 to get the 6 in total that we need. If you're dealing with a question about how many moles of an ion there is, you have to first do the valency crossover. Magnesium is in group 2, so makes 2 bonds. Bromine is in group 7, so makes 1 bond. And you swap them over, and that gives you MgBr2. Magnesium sulfate, Mg will still make 2. Sulfate you'll find on page number 9. SO4 2 minus, which means it makes 2 bonds. So the 2 negative charge tells me that. We would then swap them over, 2 and 2, cancel them out, and we are just given MgS4. Within our magnesium bromide, we have got 1 magnesium and we've got 2 bromines. Within our magnesium sulfate, we've got 1 magnesium and 1 sulfate. We're taking the whole SO4 together as a sulfate. Question says there are 3 moles of magnesium ions, and that is between the 2 substances, a mixture of the 2. It says we've got 4 bromide ions, and that only comes from the magnesium bromide. If there's 4 bromines, that means that in this chemical we need to have 2 of the magnesiums in that. That leaves us only 1 mole of magnesium to get a total of 3 in it, which means we also would need 1 mole of sulfate. That would make our correct answer A for this question. When it comes to dealing with esters, we want to break the ester link, which is a C double bond O and an O. The side with the C double bond O comes from our carboxylic acid. The other side is going to be alcohol. When it comes to naming it, we do the alcohol part first. There are 3 carbons. When we're dealing with the alcohol part of the ester, we change it to io, so this would be propio. The other side, we have 5 carbons, which would be pent. And it's pentanoate, because that's what we do with the acid side. And our correct answer then has to be E. Moving on to the next one. We are asked to work out which of these chemicals is not an isomer of this compound. Couple of options. First thing I usually do is check how many carbons are in each of them. We have 8 carbons. This one. We have 8 carbons in octan. We have 2 from eth and 6 from hex. That's also 8. Eth and hex again, that would be 8. And then meth and hept would be 1 and 7, which gives you 8. Can't rule any out in that case. I'll then go ahead and count all the hydrogens in our question. Count all the hydrogens in our compound. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, H16, and 1 oxygen. Next thing we can do is start to draw these out. We have a ketone, which means that we have a C double bond O in the middle of the compound. We have aldehyde, which means we have a C double bond O on the end of the chain. We have an alcohol, which means we have an OH group. And we have another ketone, would be our C double bond O in the middle of the chain. Counting up our chemicals, we have C8H16 and O. We have C8H16O again. We this time have C8H18O versus C8H16 with an O. Isomers have the same molecular formula but different structural formula. Answer C has a different molecular formula and a different structural formula. Another option to look at would be the fact that we have a carbon-to-carbon double bond means we have lost 2 hydrogens. The same effect would happen from the C double bond O. It reduces how many hydrogens can fit, and that would then mean that they would have similar, or in this case, the same molecular formula. So drawing them out, counting them up, and we'll get to our answer that way. Next question. We're asked here about a chemical called gabapentin. We're asked to identify the functional groups present in this chemical. First off, have a C double bond O OH. This is a carboxyl group. Means it has to be one of or C. We also have an NH2. An NH2 is called an amine group. Therefore, we have amine and carboxyl. Answer has to be A for question number 9. Moving on to number 10. Here we have phenol, and we're asked about bromine solution and hot copper oxide. We need to be aware that bromine is used best for carbon-carbon double bonds. We do have a carbon-to-carbon double bond, which means that it will decolorize. Hot copper oxide is an oxidizing agent. It's used on alcohols. This would either be primary or secondary alcohol. The carbon attached to the OH is only attached to one more. That makes that primary alcohol, which means it would have a reaction, which means that C would be our correct answer. In question 11, we're asked about degree of saturation. This means we need to consider the number of carbon-to-carbon double bonds and carbon-to-carbon single bonds. If a chemical has carbon-to-carbon double bond, that is described as being unsaturated. Unsaturated molecules, and that will react with iodine. The focus of our question is the palm oil. This means it has to have less carbon-to-carbon double bonds because it reacts with less iodine. This means that that chemical is going to be more saturated. If it's more saturated, this means that the molecules will be able to pack closer together. If they're packed more tightly together, that means they'll be stronger intermolecular forces, and this means it will have higher melting point than the other one. That all points us to the correct answer of B. For question 12, we're asked about soapless detergents. We have two parts to this. Our tail is a long covalent tail, lots of carbons and hydrogens, whereas we have an ionic head. The ionic head will dissolve in water, and the covalent tail will not dissolve in water. Something that dissolves in water can be described as being hydrophilic. So the head is hydrophilic. Look at the head, that says hydrophobic, so no, that one works. So the hydrophilic head dissolves in water, and the hydrophobic tail will dissolve in oil, and that means B is correct. B refers to the head as being hydrophilic, but it says that that means it dissolves in oil, which is incorrect. So hydrophilic head dissolves in water, hydrophobic tail dissolves in oil, and that is your answer. For our next question, we're looking for a secondary alcohol. This means that the carbon with the hydroxyl group is bonded to two other carbons. Two options for this one. If you can picture these out in your head, you can get to your answer from there. Another option is to draw them all out and then look to see which one has two carbons attached to the carbon with the hydroxyl group. In chemical A, there is only one carbon attached to the carbon with the OH. That makes that a primary alcohol. For B, we have three carbons attached to the carbon OH. That makes that, which makes it a tertiary alcohol. Next up, C, we have again one carbon attached. That means that is a primary alcohol. Whereas for D, we have two carbons attached. That means we're going to have a secondary alcohol. And that gives us a correct answer of B. In this question, we're asked about the solubility of different chemicals. We have to pair these up into things that would dissolve in water and things that would dissolve in oil. When I'm looking for water-soluble things, I'm looking for oxygens and hydrogens and see which chemicals contain those. Chemical 1, cucumber flavour, does not contain an OH group. Vanilla does. Ginger has a few of them. So ginger would be the more water soluble. Nope. In the cucumber and orange, they are made up mostly of carbons and hydrogens. Cucumber has got an aldehyde group, the C double bond O with a H, but that won't be enough to make it dissolve in water, especially when you compare it to the hydrogen bonding that ginger and vanilla are capable of because they have got that hydroxyl group. So ginger and vanilla water soluble, that makes our answer C, with the cucumber and orange being more oil soluble because they are non-polar molecules. In question 15, we're asked to name the product of the oxidation of this compound. We have got an alcohol. That alcohol will turn into either an aldehyde or a ketone. Here we have a secondary alcohol because the carbon with the OH group has two other carbons attached to it. When you're oxidizing an alcohol, you're going to turn the OH into a double bond O, and that's also going to cause you to lose hydrogen at the bottom to make space for the double bond. Here we have carbon double bonded to oxygen in the middle of the chain. C double bond O is called the carbonyl group. The carbonyl group is in the middle of the chain. That is a ketone. That can rule out these two answers because they would be aldehydes, which is not what we want in this question. Next up, this needs to take priority for numbering. This means this is carbon 1, carbon 2, carbon 3, carbon 4 and carbon 5. It's pent because there's 5 carbons. Pent 2 on because of the double bond O to the carbon on position 2. That means that this one has to be incorrect. Following through the numbering, that means that your methyl group is coming off the 4th carbon, and that gives you 4-methyl pentan 2-on. If you prioritise the methyl group, you would have ended up with answer A, but you need to prioritise the functional group, in this case the carbonyl group there. Next up, we are trying to do a titration. We're filling up a burette. You want to rinse the burette with the chemical that we are using. That means we would not want to use deionized water, which rules out these two chemicals here. We fill it to above the scale, says the same in both. Drain some of the acid and read from. It's always from the bottom of the meniscus. When we're taking the reading, we're looking at the bobbly part at the top of the liquid, and we want to take it from the base of that to make sure we get the correct value each time. So the bottom of the meniscus would be correct. Number 17, we're asked to try and separate out these chemicals called terpenes, and we're looking for the most suitable solvent. If you cast your eye across both chemicals, they are made up of just carbon and hydrogen. This will mean this is likely to be a non-polar compounds. That would mean we would want a similar chemical in order to dissolve these and separate them from the rest of the tomato juice. Ethanol is an alcohol, which means it has an OH group. This would make this a polar solvent, which would mean it's not one that we'd want to use. Pentane is just 5 carbons and 12 hydrogens. So again, that will be non-polar because it's very similar in terms of its makeup. Size is completely different, but in terms of being carbons and hydrogens, so it'd be non-polar. Propanoic acid means it's got C double bond O OH. That would then make this a polar solvent, not what we want. Water, H2O, also polar, which would not be much use for what we're wanting. So pentane would be the correct answer. Moving on to 18. Here we are asked about the reaction time of a particular reaction. We're told the concentration we care about. We want to run that up to the line. We want to run it across to find out our reaction rate. The data booklet tells us that reaction rate equals 1 over the time. We want to know the time, so we need to rearrange this. That means time will equal 1 over the reaction rate. Means time will equal 1 over 0.004. And that gives you 250 seconds. And the correct answer of D. Moving on, we are told that we've got 100 centimetres cubed of butene reacting with oxygen. Compared with the total volume of gas before a reaction, what would be the total volume of gases after the complete reaction? So what we've got is we have a 1 to 6 to 4 to 4 ratio. Our reactant are going to get used up. Our products are going to be made. They are telling us that we have 100 centimetres cubed of butene. For this to work, we'd also need 600 centimetres cubed of oxygen that we're using. And that would then produce 400 centimetres cubed of carbon dioxide, as well as 400 centimetres cubed of our water. This then tells us that our total used equals 700. our total made equals 800. That means that the made value is 100 centimeters cubed more than our starting one. So we need to use our ratios. We also then need to decipher what it's saying. It's a bit of a... The wording's maybe designed to try and trick and make you have to really think about what we're doing. But we're looking at how much we've used versus how much we've made. And we come up with our answer of A. Moving on to question 20. Here we're looking at affecting an equilibrium mixture. Sodium. We have sodium chloride, which is Na plus Cl minus. That doesn't appear to be anywhere in our equation. There are some chemicals that will have an indirect effect. It might remove something from the equilibrium, but at the moment I'm going to leave that where it is. We then have hydrochloric acid, which would provide hydrogen ions. If you add more hydrogen ions, the equilibrium shifts to get rid of them by moving to the left. That is not what we want to do. We have Na positive and OH negative. Key for this one, that is an alkali. And alkalis react with acids, which is the H plus ions. So this will remove H plus ions. This time round, we've got less H plus ions because they have been neutralized. The equilibrium therefore has to shift to the right to replace them. That is what we're looking to do because it wants the forward reaction, which is to the right. For that last one, that is CH3COO negative and Na plus. What that would do is it would provide the ethanoate ions, which is this part on the very right hand side. If you're adding more of them, equilibrium shifts to the left, which is not what we want to do. That gives us our correct answer of C. Moving on to question 21. In this question, we are told that the enthalpy of the reactants is 30 kilojoules per mole. First time I looked at this question, I got caught out by thinking that this first part was talking about an enthalpy change. So I was then going around and looking at the differences between the starting and ending chemicals, and I couldn't find anything that had 30. Then eventually clocked it just says the enthalpy of reactants. That means the left hand side is at 30. We have that for all of them, so we're not needing that piece of information at all. Next up, we want the activation energy of the forward reaction to be 110. We're starting at 30. The forward reaction would be 50, which does not match what we want. We're going from 30 up to 110, which is a difference of 80, not what we're asked about. What I think wanting people to look is just to see the value here is 110, but that's not the activation energy. Activation energy is from where you start to the highest peak of the graph, so B is therefore ruled out. Next up, we're again going from 30 up to 110. That is not a difference of 110, whereas here 30 up to 140 is a difference of 110. The reverse one, just to double check, we are starting at 70, going up to 140. That is a difference of 70. E is our correct answer. You need to be aware that that's the activation energy from where you start to the top. And if it did ask you about the enthalpy change, the difference between the starting chemicals and the ending chemicals, the reactants and the products. Moving on to question number 22. We are asked about this part of the diagram going from Z to Y. So we want to again start at Z and we want to end up down at Y. That means we have to go along this way. We then have to go from W down to X and then from X along to Y. What we should notice is that for the first one, it's the opposite way round. If I just call these 1, 2, and 3 to make it easier to refer to, that means I need the opposite. So I need negative delta H1. I am following the arrow because we're going the same way for delta H2. So that's plus delta H2. And it's same again. We're following delta H3. We're going to add that together. Putting in your values, you've got negative 210 plus negative 50 plus negative 86. You can let a data book, you can let your calculator deal with them all, or you can deal with the signs yourself. It will be 210 minus 50 minus 86. And that gives you an answer of 74. It will be positive, which means B is our correct answer. Next up, we're asked about diluting a solution. We're starting off with an ammonia solution that has 0.1 mole per litre concentration. In a situation that you're using a 50-50 split, so say 50 centimetres cubed of water and 50 centimetres cubed of ammonia, we're doing a 1:2 dilution. We are halving the concentration, so we would end up with 0.05 moles per litre of concentration. What we need to try and figure out, are we adding more water or more ammonia? Question states that we're using 50 centimetres cubed of ammonia, plus if we're filling up a 250 centimetre cubed flask with water, that means there has to be 200 centimetres cubed of water for that. That is, we have 1 part ammonia in 5 parts total, result in us having a fifth of the concentration, because there's 50 out of the 250 is the ammonia. We started off with 0.1 mole per litre of concentration, and a fifth of that would give you 0.02, or 2 times 10 to the minus 2, which gives us a correct answer of A. In this question, we are told a number of moles, we are told a mass, and we're asked to determine which chemical is our precipitate. If we know the number of moles and the mass, we can work out the GFM. N equals M over GFM, therefore GFM equals M over N. That gives you 2.868 over 0.02, and that gives you 143.4. All of the chemicals that we've got here are all in group 7. This means that they'll all make 1 bond. We have silver, which makes 1 bond, and fluorine, which makes 1 bond. When you swap over your valencies, you still get AgF. And it's the same for all of them because they're all in the same group. So that means we've got AgF, AgCl, AgBr, or AgI. If we look up how heavy silver is, which is 107.9, if we take that away from our GFM, that will leave us with the other chemical involved. Leaves you with 35.5. You may recognise that, or we can just go through each of the chemicals in turn. So we've got chlorine, which is the correct answer. Fluorine would only be 19. Bromine would be 79.9. And then iodine would be 126.9. There's involving formulas, knowing how many bonds things make, depending on our group. And that gives us our correct answer of B. And here we're adding the water. We're adding 10 centimetres cubed of water into our flask. That will be done with a measuring cylinder. Of the options, that's the better option that we've got. We are pipetting into a flask to then carry out a titration on it. That means we'd want a conical flask for carrying out our titration into. And that means our correct answer has to be A. You would use a volumetric flask to make a standard solution, which is not what we're asked to do in this one. And just in case it comes up, and standard solution is a solution of accurately known concentration. Moving on to paper 2, we're asked about diatomic elements and why they are non-polar. Non-polar means the electrons are shared equally in the bond. In diatomic elements, we have the same atom being joined together. That means that the electronegativities will be the same. In this question, we're asked to talk about this change in the size going across a period from nitrogen to fluorine. If you're going across a period, you want to talk about the number of protons. There is an increase in the number of protons. That will pull everything closer and reduce the covalent radius. That's my preferred answer. Along a period, the number of protons increases. You could also talk about there being an increased nuclear charge as a result of more protons. Next, we want a straight up definition of the first ionisation energy. Data booklet can assist partially. If we look at the equations at the top of page number 12, we can see that we are taking an electron away from an atom. We have to be talking about chemicals in the gaseous form. That's why it has a G after each of the chemicals. So we want to say something along the lines of, it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Next question, we're asked to talk about going down a group. As you go down a group, there are more electron shells. Because there's more electron shells, this will mean the electrons will be more shielded from the nuclear pool. More shells, more shielding. That would mean they would be less tightly held, and that's why the numbers have gone down. Next up, we are asked to talk about hydrogen fluoride, which has the highest boiling point out of the chemicals they've given us. We need to be able to recognise the different intermolecular forces. Here we have hydrogen directly bonded to fluorine. This means we're going to have hydrogen bonding. You need hydrogen directly bonded to F, O or N. We have hydrogen bonding. And we find that in molecules with hydrogen directly bonded to F, O or N. That's fluorine, oxygen or nitrogen. Next up, we are talking about 3 chemicals here. We're asked about the boiling points and melting points. This will be to do with their intermolecular forces. We are going to be dealing with our London dispersion forces. London dispersion forces depend on the number of electrons. If hydrogen iodide has a higher boiling point, that will mean that that has more electrons than the bromine and the chlorine. This is backed up by the data booklet, which shows that as well. Hydrogen iodine has more electrons than the others, and therefore the London dispersion forces will be stronger. In this question, we're asked to balance the equation. If we were to start off looking at the aluminiums, I'd first need to put a 2 in front of the aluminium here, which will balance out the aluminiums there. The chlorines are fine, the potassiums are fine, it's just the oxygens. Here, if we can get them both up to 12, that will give us the same number of oxygens. That means the first one needs times by 3, and the last one needs times by 4. That's going to then change my aluminium number. Now what I'd want to have is 8 aluminiums, because it's 4 times 2. We have 3 potassiums now, we need a 3 here. That fixes the chlorine problem, and oxygens we have 12 on both sides. And that would give you your correct answer. If you end up with multiples of them, so 6, 16, 6 and 8, that's also acceptable. But 3, 8, 3 and 4 would do the job as well. Next up, we are asked to do a calculation. We want the volume of oxygen produced in litres, and we're given a mass of the potassium chlorate. I'm going to start with that one first because we're asked about oxygen, so oxygen is going to be my end chemical. We've also got the mass and the GFM of potassium chlorate. So N equals M over GFM. That's going to give us 4.6 over 122.6. We take that as 0.03752. That's in moles. Next up, we're looking for our ratio. There's a 2 in front of the potassium chlorate. There's a 3 in front of the oxygen. That's 2 to 3. That could also be written as a 1 to 1.5 ratio. That means if I've got 0.03752, on the other side I need to times my answer by 2. That means I need to times my number of moles by 1.5. That gives me 0.05628. That's me now got my number of moles of oxygen. We are told the molar volume equals 24, and we want to know the volume that is produced. The molar volume means that 1 mole of the substance will have a volume of 24 litres. We have only got 0.05628. That means I want to times by 0.05628. I need to do the same to 24. So if I do my answer times 24, that will give me 1.35 litres. Another option for doing this question is to derive a formula. Is to derive a relationship from N equals M over GFM. The number of moles is still number of moles. Instead of mass, we're talking about the portion of the volume we're dealing with. GFM is the mass of 1 mole. Molar volume is the volume of 1 mole. Doing it that, then volume will equal N times molar volume, which still gives us 0.0562 times 24, which would still bring us out as an answer of 1.35 litres. Whichever way works best for you, go with it. Key would be that we've got less than 1 mole, so we need less than 24 litres. If you end up with a value bigger than 24 litres, you have mixed up your numbers. You need to have a rethink and try again. Moving on, we're asked about a catalyst effect on the enthalpy change. A catalyst lowers the activation energy. From our graph, what that would mean is that the peak would be lower. However, this question is talking about the enthalpy change, which is the part between the two platforms, the starting materials and the ending materials. And that means there will be no effect on the enthalpy change. Next one, we are told that 5.5 grams has released 103 kilojoules. And we want to know how much would release per 1 mole. So that would be 138.6 grams. I would try and go through the value 1 to get from any number to 1, you want to divide it by itself. So divide by 5.5. To go from 1 to any value, you want to times by that number. So times 138.6. That means we need to do the same to 103, divide it by 5.5, and then times it by 138.6. And I take that as 2596. So N equals M over AFM. N equals 5.5 over 138.6. We are told that we've got that number of moles gives off 103 kilojoules. So to get 1 mole, we want to divide by 0.039683. So if you do 103 divided by that number, and then we'll come out with a number that again will round to 2596. One of the things you need to watch for is if you're doing it the bottom way, you would be rounding it at some point, which then could make you come off track. If you round it too much, you might end up with a slightly different number. It should hopefully be okay, but those are the two ways that you could approach it. On to number 2. Why does increased temperature increase the rate of reaction? It increases the kinetic energy of the particles. As a result of, therefore, more particles will have kinetic energy greater than the activation energy, and there will be more successful collisions. In this graph, we're showing the different wavelengths of light emitted when different chemicals are set on fire. We are told that peak A has a wavelength of 620, but we care about peak B. Peak B is 1 box along from 600. That means we're looking for a value of around about 590. We want to go to the data booklet. We're looking to go to page 16, which discusses flame colours. It's down the bottom of that page. Chemical, the number closest to 590 would be sodium, which is 589. So the metal B would be sodium. In this question, we are asked about bonding structure and properties of compounds and how electronegativity fits into it. This means that we want to talk about ionic, polar covalent, non-polar covalent would be a good start. These all depend on the differences in electronegativity. So if the elements in a compound have the same electronegativity, they will form non-polar bonds. They will then be non-polar molecules. To illustrate our point, we can use examples from the data booklet. We have a few options. I am going to go for phosphorus and hydrogen. Phosphorus makes 3 bonds, hydrogen makes 1 bond, so it'd be pH3. If we have a small difference in electronegativity, next we could talk about the shape. If symmetrical shape, then you get a non-polar molecule. Something like carbon dioxide, there is a difference in electronegativity. The oxygen would be slightly negative, carbon slightly positive. Yeah. So it has polar bonds, but it's a non-polar molecule. So the shape that dictates that. Compared with that with something like water, and this would give you a polar molecule. Next we could talk about ionic chemicals. And that's when you've got a very large difference. And that would be something like lithium and fluorine. Lithium 1.0 and fluorine 4.0 will form from there. Then talk about intermolecular forces. They would have weak LDFs and therefore low melting points and boiling points. Polar molecules would have either permanent dipole or permanent dipole to permanent dipole or hydrogen bonding. And we need H directly bonded to F or N. We could talk about other properties related to intermolecular forces. So weak intermolecular forces would result in low viscosity, which is to do with the thickness, a high volatility, which means it's easy to evaporate. Talk about ionic compounds conducting when molten, conduct electricity when molten. And covalent compounds do not. As with all these questions, there's probably a lot more that we could write about. We only need to be good to get the 3 marks, and hopefully an answer like this would pick up all 3 marks. 3 marks for being good, 2 marks for being reasonable, and 1 mark for giving a limited answer. Moving on, we are asked about a functional group in propyl octanoate. We are looking at the C double bond O and then our O. This makes this an ester, which means it has an ester link. Next, we're asked to draw the formula for the carboxylic acid formed by the hydrolysis of the chemical. We are splitting the ester. What we need to be able to recognise is that we have our acid side on the right hand side with the C double bond O, and we have our alcohol side on the other side. We only care about the acid. I can get rid of these. The carboxylic acid would have a functional group of C double bond O, O, and then H. We've got the C double bond O part. That just means we need to put on an OH on the end, and that gives you your octanoic acid, 8 carbons, C double bond O, OH. Next up, an isomer of propyl octanoate, same functional group, was hydrolyzed. There's another ester. We've got butanoic acid, and we want a name for the other product. Right, so we have got 3 carbons here and 8 carbons there. Means we've got 11 carbons in total. Butanoic acid will have 4 carbons. That leaves us 7 carbons in our alcohol. So we are looking for an alcohol with 7 carbons. Easiest way of getting that would just be to go for hept, which is 7. Heptan, we want to put a number on it. At higher, we expect you to write where the OH group would be. We have all the possibilities that we could. I would end up just going with heptan 1 all. You could have heptan 2-ol, 3-ol, or 4-ol. You could, if you wanted to, do some sort of funky branch thing. So you could maybe go for 5 carbons, an OH on the end, and then 2 methyl groups, something like that. That would just make it more complicated to name, but it is a correct answer. So I'm sticking with heptan 1-ol. Next up, we have got a chromatogram showing the separation of fats and oils in the coconut oil. We are asked to predict the number of carbons in glyceryl trilaurate. Let's find that one. That is that chemical here. We have to use the information in the table. So, the chemical with the lowest retention time has the least number of carbons. The one with the middle number of carbons has this one here. And then finally, we have the linoleate, which is up here. Now, our one sits between the linoleate and the caprate. If we look at the numbers of carbons that we have there, we have 33 and 57. So we are looking for a value between those 2 points. It seems to be closer to the orange one because there's another chemical in between them. So we're looking for a number in between the 2 of them. I'm going to go for carbon 40. So I'm going to just say 40 carbons as my answer. When it says use the graph and the table, you need to use both of them to get the mark. Here we're asked to identify the compound which is the most unsaturated. If we had saturated carbons, each carbon would have 2 hydrogens upon it. Anytime you add in a carbon to carbon double bond, making it unsaturated, you lose out carbons. What I would do in these ones is I'd look at how many carbons there are and predict how many H's there should be. So there should be twice as many carbons as hydrogens. So if you've got 27 carbons, you should have 54 H's. This means that we've lost 4 hydrogens. Next up, we should have 66 carbons, double 33. That again means we've lost 4 hydrogens. Here we should have 114. That means that we've lost 16. That means that there must be 8 carbon to carbon double bonds because each double bond loses 2 hydrogens, and that is our most unsaturated. The one that's lost more hydrogens has to have more carbon to carbon double bonds, and that chemical is the glyceryl trilinoleate. Next one, we're asked about how you make emulsifiers. Emulsifiers are made by reacting edible oils with glycerol. How emulsifiers work is they contain both polar and non-polar parts. The polar parts will dissolve in the polar liquids, and then the non-polar parts will dissolve in non-polar liquids. You could refer to them as hydrophobic and hydrophilic. In this case, I'm sticking with the polar and non-polar. Moving on, we're asked to name this alcohol. First thing, I'll sketch it out. You have a carbon with 3 H's. You then have a carbon with a hydrogen and a CH3. You then have a carbon with 2 hydrogens, another carbon with 2 hydrogens, and an OH on the end. That gives us 4 carbons, so that's going to be bute. It's an alcohol, so it's butane. On the end carbon, that means it's butane 1-ol. The carbon branch is going to therefore be on the 3rd carbon, giving you 3-methyl bute 1-ol as your answer. Next, we're asked to complete the ion-electron equation. Currently, we have no ions. Currently, we have no electrons. We look at the two chemicals, comparing them. The difference is the one on the left has 8 hydrogens, the one on the right has only 6. That means we need 2 hydrogens in the form of H+. The overall charge on the left is 0. At the moment, we've got 2 positive on the right-hand side. We need to add electrons. The electrons go with the H pluses to balance the charge. This ensures that the little charges on both sides are both 0, and that gives you your final answer. Next question, acidified acids contain hydrogen ions. If you look at the equation, it needs hydrogen ions. Acidified potassium dichromate provides hydrogen ions for the reaction. Next one, we're talking about oxidation that we're dealing with here. This is where primary alcohols turn into aldehydes and then into carboxylic acids. Your secondary alcohols turn into ketones and then do not react again. And your tertiary alcohols do not react at all. And your tertiary alcohols do not react with oxidizing agents. Here we're asked about the colour changes that we'd see. Potassium dichromate goes from orange to green. If you were asked about some of the other ones, failings goes from blue to brick red or orange. And you have toluenes, which is the silver mirror. Next one, we're asked about the reagent that produces this. Well, that's silver. That means it's silver mirror. That means our answer is going to be toluenes reagent. Next, this chemical cannot be oxidized using oxidizing agents. Said earlier, that means it's a tertiary alcohol. If you weren't sure about that, we could do a little sketch of it out. We have an OH on the second, we have a CH3 on the second. This carbon is attached to 3 of them, therefore it is a tertiary alcohol. I just got it from the fact that it doesn't react, so that makes it a tertiary alcohol. Next, we're asked to do a ratio of oxygens to hydrogens. We'll need to sketch these out so we can see butanol is 4 carbons. We have an OH on the first one. That means that we've got 1 oxygen and we've got 10 hydrogens. Our butanol will have a C double bond O instead of the OH. That's going to be at the expense of 2 hydrogens. That means it's now a 1 to 8 ratio. And that is our correct answer there. Moving on again, enzymes. Enzymes are biological catalysts. They speed up chemical reactions within living tissues. Next up, we're asked to circle a peptide link in a protein. That is the C double bond O, N and H, which we have 3 of them. So take your pick out of any of them. Next one, we're asked to draw a structural formula for one of the amino acids used to form this section of protein. To do this, we want to split the molecule between the C double bond O and the NH. I'll draw all 3 of them so you can see which. So you can see all the options that we would have. Once we split it, we need to reform our amino group or amine group. That means that we need an NH2 instead of just an NH. So on all the left-hand sides, the way it's written, we would want to put a hydrogen on there. Next up, we want to reform our acid part, which means we need an OH on all the right-hand sides. And if you're given the option, I would go for the one on the right. It's a lot smaller, a lot less mistakes possible to make, and you would get the correct answer for any one of them. Next up, we're asked about an essential oil. Another definition: it is an amino acid that cannot be made by the body and must be obtained through diet. When you are making proteins, it's the same reaction as making esters. It is a condensation reaction. They join together and a small molecule such as water is given off. In this question, we're talking about an enzyme no longer being able to work. This happens when the enzyme becomes denatured. That happens when the hydrogen bonds are broken and the enzyme is denatured. Here, we're asked to draw a diagram showing the apparatus used to react hydrogen peroxide solution with sweet potato and measure the volume of oxygen produced. In this one, we've got the option of any kind of container we want. So we're going to want a conical flask with our hydrogen peroxide and our sweet potato. We then want to have a tube coming out. Going to carry all of the oxygen that is produced. We want to stopper that off so it only goes into our tube. We want to try and make sure we're not blocking the tube so it can still pass through. I would then use a gas syringe, easiest way of collecting the gas, especially if we have to draw it. Something like that. We would have our little graduations on them. We've got our oxygen is inside the syringe. Just for good measure, in case people think that my diagram isn't the most wonderful thing you've ever seen, and that is a gas syringe. And with a little slight adjustment, we end up with a diagram that looks something like this. It says you need to name the reactants, positions of the reactants, and naming the collected product. So we need to have all those parts in there, and that would pick up your 3 marks. 1 mark for showing your reaction happening in some sort of container or vessel. A way of collecting and measuring them. So a gas syringe works perfectly. And you also need to get the correct labels on your reactants and products. For that one, moving on. Antioxidants, they prevent oxidation of other chemicals. They react with free radicals. We want something to do with that. Antioxidants' jobs is to prevent unwanted oxidation. You could talk about the fact that without them, foods could go rancid. In this one, we're trying to explain why something is soluble in water. If we remember this structure of water, water is a polar molecule. This means this chemical must have lots of polar groups. In fact, it's got 4 hydroxyl groups. Therefore, it is also a polar molecule. And it can form hydrogen bonds with the water. They've both got OHs. And that's what allows them to dissolve together and picks up 2 marks. Next one, we are doing one of the scaling up ones using proportions. We are told that we have 3 milligrams in 1 kilogram body weight. And we are told we have actually got 65 kilogram person. We are scaling up and we multiply by 65 because it's 65 times bigger. So we do the same on this side, times 65. That should be 195 milligrams for the 65 kilogram person. Next, we're told that there's 0.2 milligrams in 1 gram, presuming that's of potato, in 1 gram of potato, whereas we want 195 milligrams. Well, I say want, that would provide the toxic dose. Maybe we don't want to poison someone. If we go through the value of 1, to go from 0.2 to 1, you could times it by 5. I always like to do the same thing, which is divide by that number to bring it down. So divide by 0.2, and to go from 1 to 195, it's times 195. So we have our 1 gram of potato, divide it by 0.2, times by 195. And that will give us 975. And that would be in grams because it's the grams of potato. That picks up 3 marks for that one. In number 7, we're using a fuel to raise the temperature of water. This means we're going to be needing to use EH equals CM delta T. Well, first, we'll work out the energy that was released from however much fuel we used. So EH equals CM delta T. EH we're working out. C for water is 4.18. It's in the data booklet. We need to turn this into kilograms. So it would be 100 grams. 1 centimeter cubed is roughly 1 gram. And that would be 0.1 kg. 0.1. And we're raising the water by 27. That's your delta T. Therefore, our EH equals 11.286. That would be in kilojoules. We're told the enthalpy of combustion is 891. That means that 1 mole would need to give off 891 kilojoules. And we're trying to work out how much we would actually have burned of the methane, because we know we want to give off 11.286 kilojoules. Sticking with the scaling thing that works nicely for me, divide by 891 gives you 1 kilojoule, and then times by 11.286. We do the same on the other side for our 1 mole. We're going to have 1 divided by 891 times 11.286. That means that we've got 0.0127 moles of methane. 0.0127 moles. Then we want the mass, so mass equals N times GFM. M equals the number we just worked out, times methane is CH4. That's 1 carbon, which is 12, and 4 hydrogens, which are 1. That gives you a total of 16. Times our answer by 16, and that gives you 0.203. And that again would be in grams. The way I've seen people do it as well is they talk about the fact that your enthalpy change, which is delta H, equals the energy change over the number of moles. And that's just doing the same sort of calculation, just in a slightly different order, and would still bring out the correct answer. That's the way you like to do it. Go for it. Next one, we're asked about bond enthalpies of these chemicals. We need to be able to picture what these look like. We've got methane, which is carbon and 4 hydrogens. Oxygen is a double bond between the oxygens, and we have 2 of them. That's going to make up my breaking part of it. bonds we're breaking. So we're going to have 4 times whatever CH is and 2 times whatever O double bond O is. Over to the other side, we have got carbon dioxide. Spoke about this earlier. It was C double bond O on 2 sides. That means that we're going to need to do 2 of the C double bond O's, and that's for our making. And then water, H2O, that's 2 H2O bonds, but there are 2 of them. So we're going to need 4 times H2O bond. We can then go into the data booklet and find these values. We're breaking oxygen bonds and C to H bonds. That's 412 and 498. And we're making C double bond O, and we're also making OH. That's 804 and 463. If we total them up, that gives you 1648 plus 996. Gives you 2644 on the left hand side. Other side we have 1608. We would then have 1852. Gives you 3460. To break bonds, you have to put energy into it. This makes that a positive enthalpy change. When you make a bond, you release energy, which would mean we'd release 3460. And popping that into our calculator gives us our final answer of minus 816 kilojoules per mole. Next question wants us to work out the atom economy of this reaction. We go to the data booklet. Here we're told percentage atom economy equals the mass of desired product divided by the total mass of reactants. Our desired product is hydrogen, which is over here. Key to these questions, you must take into account any balancing numbers that there are. That means that on the top line we're going to have 3 times 2, 3 hydrogens, and there are each GFM is 2, divided by, we need to do the same for our reactants. There's only one of each of them, so we just have to add 16 and 18 together. That times 100. Top line would be 6, bottom line will be 34, times that by 100, and that gives you a final answer of 17.65, and that would be in percent. Next, we're talking about our equilibrium. We need to recognise that a negative enthalpy change means it's exothermic. If it's exothermic, that heats the surroundings. When would you want to heat the surroundings? You'd want to heat the surroundings when it is cool. And I've just spotted they're trying to trick us because they are talking about the nitrogen dioxide. So if this way is exothermic, and that would be favoured by cooling, we are asked about the endothermic version, which would be favoured by a high temperature. Depending on which chemical we're favouring, it changes our answer, so that should be a high temperature. In terms of pressure, we need to think about the moles of gas. We have 2 moles of gas on the left, but only 1 mole of gas on the right. We want to favour the larger side, which means we want a low pressure. I think about, if we're using our hands, if we want to increase the pressure, we need to lower the volume. There's less space between them. We're squashing them together. We want to favour the bigger side, so a lower pressure would allow us to do that. This question is a Hess's law question, and there's a lot going on here. The way I approach this is I look for the first chemical in our target equation. That's the chemical we're trying to find out about. I try and find which equation is that found in, and that is found in equation 1. And in equation 1, it's on the wrong side, and it's also, we need 4 of them, and there's only 1 in that equation. Because of that, what I'm needing to do, I want to be flipping it round and timesing by 4. To make it easier to keep track of, what I would do is I would write out that we need negative 4 delta H1. Next up, go on to the next chemical. And that's going to be N2O4. When I look for it, we have it in this equation here. It is on the wrong side again. We need 5 of them this time. That's going to be negative 5 delta H2. If we keep on going, we will then get to our carbon dioxide. And our carbon dioxide gas is found in the third equation. It is on the correct side, but it's not the correct number of them. That means I'm going to add it, but I'm going to add 4 of that equation together. Next, we have water as a gas. And that appears in only the last equation. It's on the correct side, but we need 12 of them, so it's plus 12 delta H5. Then when it comes to the last one, that is the nitrogen. And nitrogen appears in 2 equations. Because it appears in 2 equations, that means I'm not going to touch it. I'm going to leave it alone. And what will happen is that will just work its way through. What I'll do in a minute is I'll rewrite everything out and I'll show you how it all fits together. But if it appears in 2 equations, we are best just leaving it alone. We've not used all the equations yet. So I need to try and think of, well, how am I going to use delta H4? What I'm spotting in delta H4 is that we've got water as a liquid, we've got hydrogens as a gas, and we've got our O2. The purpose of this one is to get rid of the hydrogen from the first equation, because that's no longer there, and also to get rid of the liquid water from equation 5. And to do that, what we would need is we would need to have 12 waters, which would cancel out the waters from delta H5. Because what we did is I have times this one by 12. And I would want to keep it this way round because I want the water that's a liquid on the opposite side from this one. For our first equation, we flipped that round, so the hydrogens would be on the right. So we want to keep these hydrogens on the left because they will cancel out. What we would do then is we would want to keep it in the same way round so it's positive, but we want to have 12 delta H4. At this point, what we could do is we could just throw in all the numbers and hope that we've got them arranged in the right way. Times the ones we need to times by the right numbers. We'll flip the ones we need to flip. What you can do, and for this one, I'm a bit put off it because there's so many things to keep track of. But what we could do is write out our new equations after we've flipped them or we've multiplied them up. So that's what I'm going to do now. And then I'll show you how it all plots together. First equation we flipped and times by 4. Our second equation we flipped and times by 5. The third one we have just times by 4. The last 2 equations we have just times by 12, keeping them on the same side. A half times 12 would give you 6 oxygens. If we have correctly arranged these equations, when we cancel out things that appear on both sides, we should be left with this top equation. If it is not left with the top equation, we have messed something up. Looking for things that are appearing on both sides, we have 4 carbons on each side. We have 12 hydrogens here, and we have 12 hydrogens there. We have 4 and 6 oxygens, which is 10, which gets rid of this 10 oxygens there. We have our 12 waters as a liquid, which can cancel it as well. And that, and the last thing we need to do is we have 5 and 4 nitrogens there, which gives you a total of 9 nitrogens. So when we go up to the top, so when we go up to here, we're supposed to have 4 of them, we do. We're supposed to have 5 of them, we do. We're supposed to have 4 CO2s, we do. We're supposed to have 12 waters of gas, we do. And we're supposed to have 9 nitrogens, which we do with the 4 and the 5. And that's what I was saying earlier, it fits itself, it fixes itself as you work through. That means that we have the correct relationship between the different values. If you find that that's going to take too long a time, it's quite a bulky example of this type of question. We could just put the numbers in and hopefully we've got them arranged correctly. All I'm going to do now is going to substitute in my values. We have -4 of delta H1. So that's now going to be a negative enthalpy, and that's going to be 216. Next up, we have 5 of the -20s. So we have negative 100 or positive 100 for that one. Next one, we've got 4 of our next one. 4 times negative 394 will be negative 1576. Next, we've got 12 times the negative 286. That gives us negative 3432. And then we've also got plus 12 times 41. And that gives you 492. And then that just leaves us to put them all together. And that gives us our final value of negative 4632 kilojoules as your answer. Next one, we have to draw out a formula for this chemical. We need to remember that carbon needs to make 4 bonds in total. Nitrogen in group 5 so needs to make 3 bonds. And hydrogen needs to make 1 bond. We're given the shortened structural formula. We could just follow that through. We need a carbon with 3 hydrogens on it. Like so. We need a nitrogen with 1 hydrogen. We need a nitrogen with 2 hydrogens. So each thing's making the correct number of bonds. All works together. That picks up your mark there. Okay, in this question we're told there is a catalyst for this reaction. We have to talk about the effect of catalyst. The catalyst increases the speed of both the forward and the reverse reactions, which means it has no effect on the position of equilibrium. It stays the same. It favours both the forward and the backwards. Next one, we have a chemical which is exothermic, which means that it's favoured by cooling, as it gives out energy. So that means we want it to be higher at the low temperature and then lower at the high temperature. So we want a value, we want a graph that's sloping down the way. And that gives you a decrease in yield as the temperature increases. Okay, so in this question we're asked to determine the limiting factor. I want the number of moles of both of the chemicals. I'll start with the sorbic acid first of all. We can use N equals M over GFM, so N equals 7 divided by 112. That gives you 0.0625. For potassium hydroxide, I'm going to use N equals C times V. Turn your volume into litres by dividing by 1,000. And then half of 0.25 will be 1.25 moles. Next, it's important that we think about the molar ratio. If you don't consider the molar ratio, there's a risk that we pick the wrong chemical as our limiting factor. It is a 1-to-1 ratio. If I want to use all sorbic acid, all 0.0625, I would need the same quantity of the potassium hydroxide. This is what we have got of each chemical. We do have enough for that to work. And if we do that, that means that all the sorbic acid is used up. If we tried to use all potassium hydroxide, which is 0.125, we would need that same quantity of the sorbic acid. We do not have enough to make that happen. That means that our sorbic acid is our limiting factor. Taking into account the molar ratio, there are less number of moles of sorbic acid. It's going to run out quicker. The sorbic acid limiting factor. Right, so in this question, we are told that a 1% solution has 1 gram in 100 centimeters cubed. We are told we want a 0.002% solution. Therefore, that would then have 0.002 grams in 100 centimeters cubed. We want a 330 centimeter cubed can of this. So that means if we've got 0.002 grams in 100 centimeters cubed, then we want to divide by 100 to tell you what would be in 1 centimeter cubed. And then we want to times by 330. We do the same on the far side, 0.002 over 100 times 330. And that gives 0.0066 grams of ammonium ferric, or ferric citrate, I should say. Final question, we want the number of moles. Moles equals mass over GFM. All the same chemical, so we don't need to worry about any ratios. It's going to be 0.0066 divided by, question tells us GFM is 261.8. And that will give us an answer of 2.52 times 10 to the minus 5. Or 0.000052 moles. That would be our answer. Next up, we're asked about a property of an essential oil. An essential oil is a volatile, non-water soluble, aroma compound. So any of those three would work out from there. We're talking about isoprene. Isoprene units make up terpenes. Next, we're asked to draw the structure of isoprene. Isoprene, here they're calling it 2-methyl-1,3-butadiene. Sometimes can also be called 2-methyl-buta-1,3-diene. That means we've got 4 carbons in the longest chain. We have 2 double bonds between carbons at position 1 and position 3. We have a carbon coming off of the second. We need to make sure that each carbon is making 4 bonds, and that would give you your structure that looks like that. Isoprene units, there are 5 carbons in each unit. We go up and we count how many carbons we've got. We've got 1, 4, 5, 6, 7. So there's 15 carbons, which means there has to be 3 isoprene units, which gets us our answer there. This question, we try and spot the difference to see what has been chopped out, of this chemical. The double bond's the only thing that's different. So I'm looking at this section of the chemical, which is up here. It has to have lost an OH and a H. That makes our product water. The reaction is a dehydration, where water is removed and a carbon-to-carbon double bond has been made. To name functional groups present in 2 of the chemicals and not in the third chemical. Have a look. So options for functional groups. So these both have got hydroxyl group. They have both got a carbonyl group. Don't see any other ones they've got in common. Well, they've got this thing, it's called an ether, but you don't need to know about that. If we go up and look at this chemical, there's no options at all, so hydroxyl and carbonyl will pick up your points. Just make sure you're looking at the correct 2 chemicals. In this question, we're asked to describe how we could get the actual yield of a reaction. If we look at the first experiment, we'll notice that they are making a solid. What we could then do is, if we carry out the reaction, you want to filter the precipitate and then measure out the mass. In the second one, we are making a mixture of liquids. So you'd carry out the experiment and then separate using distillation. And that's an ester, and that's from water. When you're using a condenser, you want to have the water in at the bottom and out at the top. That will help give maximum cooling and get them separated out properly. They have differences in boiling points, and that's why this would work out quite nicely for that. Next one, we are making a gas. That gives you a couple of options. You could carry out a reaction and measure the change in mass as the gas escapes. And this would be the mass of hydrogen that's given off. Or you could collect the hydrogen in a gas syringe and measure the volume that was produced. These actual values could be compared to the theoretical yield and use the percentage yield calculation. with the open-ended questions. 3 marks for a good answer, 2 for reasonable, 1 for limited. I'd hope that would pick up all 3 marks. I've quite possibly missed things we could have talked about, but that's everything that sprung to mind. In A part 1, we're asked to focus on chemicals 3, 4 and 5. The differences in these ones are the number of fluorines or the number of chlorines. I'm going to focus on the fluorines. More fluorine atoms decrease their oxygen depletion potential. Next up, which pair of compounds should be used to show the effect of replacing chlorine with bromine atoms? So we want the only difference to be chlorines for bromines. Have a look there. 1 and 5 would be a good shout. That's the only difference. 2 bromines over 2 chlorines. 1 and 5 would work out. Next, we're asked about 2 other chemicals and why they would have 0 as their oxygen depletion potential. When we look at all the ones in here, the thing they all have in common is they all have a chemical from group 7 in them, be it chlorine or bromine or fluorine or all 3. These ones do not have any of them, so they do not contain any group 7 atoms or halogens. Free radical is a substance that contains an unpaired electron, not a 3 electron, an unpaired electron. In this one, we are producing radicals. This means this has to be the first step in the reaction, which is an initiation reaction. In a propagation step, there will be free radicals on both sides. If we are using a fluorine radical, I'm going to react it with the CH3F that we've got at the start. My radical this time would be my CH2F. And the fluorine radical would have picked up a hydrogen to become hydrogen fluoride. Just be HF. You could pick other chemicals that come together, join them up if you want to, but we need to make sure that we've got a radical on the left and a radical on the right for it to be a propagation stage. In this question, we're told about refrigerants. Okay, here we want to know about pentafluoroethane. Make 0.05 kilograms of coolant. It's 50% of each. Okay, so 50% of the 0.05 kg, that would be half of it, so 0.025 kilograms. And then we've got our GFM, so 0.025 kilograms. If you times it by 1,000, that would give you 25 grams. And we want number of moles, so number of moles equals 25 over the GFM of that chemical, which is 120. 25 over 120 gives you 0.208 moles as your answer. For that one, yeah, 50% of it. Get it into grams because you're using GFM, and that works out. Next one, we've got salt being made. Right, so it's acid plus base makes salt plus water. We also make carbon dioxide because it's a carbonate. So they have told us the salt is this thing. So it's going to be water and carbon dioxide. Next up, we're to do the ionic formula of copper ethanoate. Copper has a valency of 2, as it says here. That means it's got to be a 2 positive charge. For ethanoate, we can get that from the data booklet. The data booklet says that it's CH3COO negative. For the formula to balance out, we need to have 2 of the ethanoates, because then you get your 2 negative charge that will balance it out. That would be Cu2 plus CH3COO negative, but we need 2 of them, and that will be your correct answer. Another option of how to tackle that question, if we go through how we would do a normal valency crossover. Oh, that's that. So copper makes 2, that makes 1. Swap them over, it gives you 1 and 2. Cu CH3COO in brackets, and there's 2 of them. Then we can go back and think, well, the metal has to be positive, and the other one it said in the data book it was negative. So then you'd put in your 2 plus and your negative to get the same answer we've got. Either way, that is the correct answer. We are preparing a standard solution of a chemical here. In this question, we're told we've already got our known mass of the sample. The first thing we need to do is dissolve it in a small volume of water. We'd want it to be deionized or distilled. We then want to transfer into a volumetric flask with rinsings. So we add more water once we've transferred it. So transfer with rinsings to a volumetric or standard flask. And then you want to make it up to the mark, fill it up to the mark, whatever you want to say, with some more water. You then want to stopper it and then invert it to mix. And that would pick up those marks there. In this one, we're still in the midst of the titration. We're asked to draw a pipette. So with our pipette, we've got our straight lines there. We've then got the bulby part, and that comes down to more straight lines with our tips. And we need our line for where we'd fill it up to. And with a little bit of rearranging, you end up with something that looks a bit like this. The next one, we're asked about an indicator. We're told the colour changes that happen. In our reaction, we are starting with an alkali and we're adding acid. With an alkali, it says it's pink, and acid is in neutral, it will be colourless. This means we have to go from pink to colourless. Next question is the term for values within 0.2 of each other. That is just the word concordant. Our final question is to do with calculating concentration of a chemical when given volumes and concentrations. We're going to start with oxalic acid. In oxalic acid, we're told the concentration in the volume. Concentration is 0.126 moles per litre. They give you 2 volumes, you need to be careful that the oxalic acid volume is the 26.75, 0.02675. That gives 0.003705 moles. We're comparing 2 different chemicals, so we want to use a ratio. Question states that sodium hydroxide was titrated with oxalic acid. This is our sodium hydroxide, sodium hydrogen oxygen. This means that this is our oxalic acid. It's a 1 because there's no number in front of it. A 2 because there's a 2 there. That means we want to double our value of number of moles, 0.006741. And then last of all, we want to work out the concentration of sodium hydroxide. If N equals CV, then C equals N over V. That equals 0.006741 divided by 25 centimeters cubed, or 0.025 litres. And then final act of the day, get that there. I'm going to round it to, I would round it to 3 significant figures. The 6 will round up, so it will be 0.27 or 0.270. And that's going to be your moles per litre. That brings us to the end of the paper. That's how I would approach each of the questions. Thanks for watching. Goodbye.